What if the sky above us is not simply a map of stars, but a memory system, replaying cosmic events that once shaped the earliest civilizations long before the age of dinosaurs? What if the rare alignment now unfolding as Comet R2 SWAN reveals an unexpected twin sunward tail and the interstellar traveler 3I Atlas intensifies its approach near Earth is not a coincidence of celestial mechanics, but a signal repeating through deep time? These two luminous wanderers, crossing paths on a scale older than continents, seem to echo patterns found in ancient mythologies, geological anomalies, and symbols carved into stone by cultures who should have known nothing of interstellar visitors. Yet they did. Again and again, ancient societies described split-tailed stars and foreign comets that arrived from the dark between worlds. Their stories survived extinction events, tectonic reshaping, and the erasure of early human memory. What were they trying to tell us? And why do these same patterns appear now, in our lifetime, precisely as R2 SWAN and 3I Atlas converge? Tonight, we explore a hypothesis that merges astrophysics, prehistoric time cycles, and the possibility that Earth once hosted forms of intelligence so ancient they predate biological evolution. As R2 SWAN stretches two luminous tails toward the sun, one shaped by radiation pressure, the other by forces science still debates, we find ourselves facing a mystery as old as the planet. Twin-tailed comets appear in carvings from civilizations separated by oceans and epochs. Some portray them as omens, others as visitors, some as teachers. Could these celestial alignments be reminders of lost time, fragments of a cosmic story Earth once understood? And what about 3I Atlas, the interstellar object whose acceleration and chemical composition defy standard comet behavior? If this visitor truly originated beyond our solar system, then its arrival now, synchronized with another anomalous comet, forces us to ask whether these alignments follow cycles not measured in human centuries, but in planetary ages. If this mystery resonates with you, tell me in the comments what you believe comets truly represent in Earth's ancient story. Do they warn, guide, or remember? Your perspective may help unlock the next piece of this cosmic puzzle. And if you want to continue exploring the forgotten relationships between the sky above and the worlds that existed before history began, like this video and subscribe. It supports this channel and keeps this community of seekers growing as we uncover what may have been hidden in the heavens since. If we follow the path laid out by these celestial visitors, we are forced to look deeper into the Earth's own early story, into eras so ancient that even fossils hesitate to speak. When Comet R2 SWAN reveals a twin sunward tail, bending light and solar wind into two separate luminous paths, it is not only a moment of astronomical interest, but a reminder that the cosmos has been performing such alignments for billions of years, long before human consciousness ever arose. And if 3I Atlas, an interstellar traveler not born of our sun, now intensifies its alignment with Earth's orbital plane, then these two objects may be reenacting a pattern that once shaped the planet itself during a time when life was still a whisper waiting to form. The early Earth was a world of molten seas, volcanic continents, and an atmosphere thick with energy and potential. In this primordial environment, the sky did not simply decorate the world, it sculpted it. Comets brought water, organic molecules, and perhaps even the first seeds of chemical memory. Their trajectories carved invisible signatures into Earth's magnetic field, leaving imprints that may still echo today. And if twin-tailed comets or interstellar objects once passed near Earth in cycles far older than any written record, then perhaps these events became part of the planet's evolutionary rhythm, triggering geological shifts, magnetic reversals, or subtle changes in the atmosphere that influenced the rise and fall of ancient forms of awareness. Scientists traditionally view prehistoric Earth as a world devoid of consciousness until biology emerged billions of years later. But what if consciousness, in some early form, existed before biological life? What if it was woven into the electromagnetic grid of the planet, encoded in the crystalline structure of minerals, or resonant in the plasma storms that raged across the early skies? If the earliest forms of intelligence were not biological but environmental, then celestial alignments, particularly rare and dramatic ones, could have acted as catalysts, activating or disrupting vast planetary networks of awareness. Imagine a world where intelligence did not speak or see or move as organisms do, but pulse through mineral matrices and magnetic fields. In such a world, the passage of a comet with a bifurcated tail, or the intrusion of an object from another star system, might have been perceived not as a visual event, but as a shift in consciousness itself. An awakening, a disturbance, a signal. This possibility opens a new perspective on the enigmatic patterns found in ancient rocks and early sediments. Some layered formations bear geometric impressions that resemble energy flows more than biological fossils. Others show branching structures reminiscent of lightning strikes, plasma discharges, or resonant interference patterns. These shapes have puzzled geologists for years because they do not match typical mineral or biological processes. If ancient Earth hosted a form of pre-biological intelligence, its interactions with celestial events may be recorded in these rocks as patterns of energy fossilized over billions of years. Comet R2 SWAN's twin tail is a vivid analogy for this idea. The primary tail, shaped by solar radiation, is predictable, but the secondary sunward tail, arcing toward the sun against expectation, suggests interactions with fields or forces not fully understood. Some astronomers believe this is caused by ionized particles escaping in complex directions. Others suggest dust grains behaving unpredictably. Yet the phenomenon remains rare and symbolic. Two paths emerging from one object, moving in opposite directions, as if reflecting the duality of memory and transformation. In ancient mythologies, dual-tailed comets were often associated with creation and destruction, with cycles of renewal that predated the civilizations who later recorded the stories. If these myths echo a memory older than humanity, perhaps rooted in the earliest forms of planetary awareness, then R2 SWAN's twin tail is a reminder rather than a coincidence. And then there is 3I Atlas, whose very presence challenges our assumptions about cosmic isolation. Interstellar objects do not obey the evolutionary history of our solar system. They bring with them chemical signatures from worlds and stars we will never see. Their trajectories are shaped by forces that acted long before Earth existed. When such an object aligns with Earth and another comet at the same time, the statistical improbability raises questions. Not questions of danger or prophecy, but questions of memory. What cycles of alignment existed in the deep past? Did these events coincide with key transitions in Earth's geological or atmospheric evolution? Could they have played a role in the emergence of early chemical systems that later gave rise to life? Some researchers studying prebiotic chemistry propose that comets may have acted as carriers of information, not in a digital sense, but in the way complex molecules can encode patterns and trigger reactions. If interstellar comets seeded Earth with molecules shaped by alien environments, then life on Earth may carry within it the faint signatures of cosmic ancestry. These molecules may have interacted with Earth's early mineral networks, creating the first templates of replication and memory. In this view, celestial alignments are not passive events, but active catalysts. And if consciousness eventually emerged from those templates, then it is not unreasonable to wonder whether early forms of awareness on Earth may have been influenced by celestial patterns, repeating across millions of years. Perhaps these alignments triggered environmental changes that nudged evolution forward, or awakened dormant potentials within mineral structures that later harmonized with biological life. The fossils of enigmatic Precambrian organisms, fractal beings with no clear evolutionary ancestors, may be remnants of life shaped by forces beyond the Earth itself. Their sudden appearance and disappearance mirror the unpredictable nature of cosmic events, as if they bloomed in resonance with something passing overhead and faded when that resonance was gone. Such organisms, with their strange symmetry and impossible geometry, may reflect the influence of early celestial patterns interacting with environmental intelligence. As R2 SWAN and 3I Atlas now trace paths across our sky, their alignment may remind us that Earth still participates in cosmic cycles far older than life, cycles that once shaped the planet's earliest expressions of awareness, and may yet hold clues to understanding why intelligence emerged at all. To explore these clues, we must look more closely at how celestial phenomena sculpted Earth's prehistoric landscapes and influenced the rise of if celestial forces shaped the earliest conditions for life. Then it becomes necessary to consider how Earth's mineral world responded to these influences with a complexity that hints at more than passive interaction. Minerals are not inert. They grow, fold, branch, conduct electricity, generate magnetic fields, and store information at the atomic level. In the prebiotic Earth, long before cells emerged, the mineral kingdom formed intricate networks that may have acted as early processors of environmental data. The alignment of comets, especially objects with unusual electromagnetic properties like 3I Atlas, would not simply glide through space unnoticed by this proto-intelligence. Their charged tails, magnetic signatures, and gravitational influences could have rippled through Earth's mineral structures, creating patterns of stress, vibration, and resonance that subtly reshaped the foundations from which life would one day arise. This idea is not mystical. It is grounded in the study of piezoelectricity, crystal growth under electromagnetic fields, and the emerging field of quantum geology, which examines how minerals store and transmit information. When a celestial object passes overhead, especially one carrying interstellar dust with unfamiliar magnetic signatures, the Earth's crust and mantle respond. They tremble, they charge, they reorient. And such microscopic changes may have accumulated over millions of years, weaving a tapestry of influence that set the stage for the first self-organizing chemical systems. In some regions, mineral formations appear almost too structured to be purely accidental. Hexagonal columns, fractal branching patterns, mysterious cavities lined with geometrically perfect crystals. While these can be explained geologically, they also reveal how matter naturally organizes itself into shapes that resemble early biological structures. In a world without life, minerals were the architects. They built repeating lattices, etched symbols of symmetry into the planet's crust, and formed channels that guided electrical currents through the Earth's early environment. These currents may have behaved like neural pathways long before neurons existed. Some researchers propose that these mineral pathways could have acted as primitive memory systems, storing information about environmental cycles. If true, the early Earth may have had a capacity to remember, long before the first organism opened its metaphorical eyes. Now consider how comets fit into this picture. The passage of a large celestial body with a tail of ionized gas introduces new variables: electrical currents, charged particles, complex chemical compounds, and gravitational perturbations. When Comet R2 SWAN displays a twin sunward tail, it indicates interactions with solar and possibly interplanetary magnetic fields. These interactions radiate outward, they travel across space, and when they reach Earth, they do not arrive as harmless streaks of light. They arrive as electromagnetic waves, altering the balance of the planet's upper atmosphere, stimulating auroras, charging the crust, and subtly influencing the electrical properties of the mineral networks below. Early Earth, rich in conductive surfaces and crystalline structures, would have responded strongly to such events. If the planet's early mineral networks acted as proto-neural systems, then comets may have served as external stimuli, electrical impulses delivered across millions of kilometers. Each alignment, each pass, each cosmic encounter could have contributed to the gradual emergence of self-organizing systems that later blossomed into life. This concept aligns with the idea that environmental complexity drives evolutionary leaps. But evolutionary leaps need triggers. They need moments of energetic imbalance, moments where the environment is pushed out of equilibrium. Comet alignments provide such moments. They create temporary windows of increased chemical potential, altering the stability of molecular structures. In a young Earth teeming with volatile compounds, these windows may have allowed new configurations of matter to form, configurations that eventually led to metabolic cycles, replication mechanisms, and the earliest forms of biological awareness. It is also possible that interstellar objects like 3I Atlas carried molecular fragments or structural templates that interacted with Earth's minerals in unique ways. Studies of meteorites reveal complex organic molecules, including amino acids and nucleobase analogs, embedded within them. These molecules did not originate on Earth, they came from distant regions of the galaxy. If such materials were delivered during a period of celestial alignment, the resulting chemical and electromagnetic interplay may have produced conditions that allowed life to emerge from non-life. But perhaps more intriguingly, these interactions may have left behind imprints, patterns encoded in minerals that record not only chemical information, but also energetic signals from the cosmos. Some crystals, such as quartz, can trap electromagnetic vibrations in their structure. Over billions of years, these vibrations may be preserved as faint signatures of ancient cosmic events. Studying the magnetic memory of rocks reveals anomalies, regions where magnetic grains are aligned in ways that differ from the surrounding geological context. These anomalies often align with periods of intense celestial disturbance. What if these magnetic signatures are the fingerprints of cometary alignments, storing information from eras so old they precede biological evolution? If the Earth's mineral world contains a record of such events, then the story of life's origin is not limited to chemistry, it is intertwined with astronomy. The planet itself may be a library of cosmic influences, each geological layer a chapter written by celestial encounters. This perspective also helps explain certain puzzles in evolutionary history. The sudden appearance of complex organisms during the Ediacaran period, the sporadic leaps in genetic complexity, and the mysterious disappearance of entire lineages may reflect not only earthly conditions, but also cosmic catalysts. If comets delivered both energy and information, aligning with Earth's internal cycles, they could have played a role in directing evolution's path. Ancient cultures intuitively understood that the sky influenced the Earth. Their myths describe the heavens interacting with the ground, shaping destinies, creating floods, igniting fires, awakening forgotten powers. While these narratives are symbolic, they may echo a deeper truth, that celestial patterns have always been part of Earth's evolutionary rhythm. And now, as we observe R2 SWAN and 3I Atlas creating a pattern not seen in recorded history, we are reminded that cosmic cycles continue, whether or not we understand their significance. To grasp that significance, we must look not only at minerals and chemistry, but also at the strange organisms that emerged during Earth's early eras, whose forms challenge our understanding of life itself, and whose existence may hold the next piece of this unfolding mystery as we move toward. To understand these strange organisms, we must travel into the deep shadows of the Ediacaran and Precambrian eras, where life appeared not as familiar creatures, but as geometric enigmas. These beings, some shaped like fractals, some like ripples of light frozen into tissue, do not fit easily into the tree of life. They rise abruptly in the geological record, flourish briefly, and disappear without leaving descendants. Their existence is a puzzle that forces us to question the simplicity of early evolution. Some of these forms, such as the iconic Dickinsonia or the oddly geometric rangeomorphs, appear almost too structured, as if guided by principles beyond biological instinct. They exhibit fluid symmetry, branching ratios that mimic electrical discharge patterns, and growth habits that resemble fractal mathematics more than cellular division. Scientists often describe them as problematic forms, a term that captures both the mystery and the discomfort they evoke. These organisms challenge the narrative that life developed incrementally. Instead, they suggest waves of experimentation, developmental blueprints suddenly appearing as if triggered by something external, rather than purely terrestrial processes. If we consider the influence of celestial alignments during this period, a provocative idea emerges. These enigmatic life forms may have arisen during cycles of heightened cosmic interaction, times when comets or interstellar objects passed close to Earth, altering atmospheric chemistry and electromagnetic conditions. Studies of ancient sediments reveal spikes in isotopes associated with cosmic influxes, indicating that Earth periodically received bursts of radiation or extraterrestrial material. These spikes often coincide with periods of evolutionary innovation. The organisms that emerged during these times seem to reflect the environmental disturbances that may have shaped them. Their bodies often lack mouths, organs, or internal structures. Instead, they absorb nutrients through broad surfaces, as if their existence depended more on field interactions than biological machinery. This suggests that life, in its earliest complex forms, may have been influenced by environmental fields, electrical, magnetic, or chemical, created or intensified by celestial events. Imagine an early Earth where each cometary passage altered the electromagnetic landscape, stimulating new forms of growth in organisms responsive to ambient energy. Their shapes, radiating, branching, spiraling, mirror patterns seen in plasma physics, lightning filaments, and magnetic field lines. In this sense, these beings were more like embodiments of environmental conditions than independent entities. If their existence was tied to cosmic rhythms, then their disappearance may have occurred when those rhythms shifted. As cometary alignments faded and Earth stabilized into more predictable cycles, these early forms may have lost the environmental conditions that sustained them. Their extinction would not be evidence of failure but of transformation, an evolutionary handoff to new forms capable of thriving in a changing world. This leads to a compelling possibility that early life did not evolve in isolation, but in dialogue with the cosmos. Where modern organisms adapt through genetic mutation, these ancient beings may have adapted through environmental resonance, their bodies responding to the frequencies and energies present at the time. This idea challenges conventional evolutionary theory, but aligns with observations from fields as diverse as geobiology and astrobiology. Some modern organisms, such as extremophiles, still display sensitivity to electromagnetic fields, radiation gradients, and mineral surfaces. If life today retains faint echoes of such ancient responsiveness, then the strange organisms of Earth's early eras may represent a lost branch of evolution shaped by cosmic forces. The existence of these forms also raises deeper questions about intelligence. Not intelligence as we understand it, brain-based, symbolic, linguistic, but a form of environmental intelligence embedded in patterns. The fractal organisms of the Ediacaran appear to follow algorithms of growth that maximize efficiency, surface area, and structural integrity. These algorithms mirror patterns found in resonant systems, from sound waves to electromagnetic fields. If these organisms arose through interactions with celestial influences, then their complexity may reflect information carried by those influences. Comets like R2 SWAN or interstellar objects like 3I Atlas may not simply deliver materials, but patterns, templates, or energetic signatures capable of guiding self-organization. In this view, the cosmos becomes not only a source of raw ingredients, but a teacher, imparting structural logic through repeated interactions across deep time. This hypothesis finds support in the discovery of unusual microscopic fossils, spiral filaments, concentric rings, and nested geometric structures that defy classification. Some appear to have grown in ways that resemble standing waves or interference patterns. If early life responded to dynamic environmental fields, then these shapes could be the fossilized remains of energy-driven growth. As celestial alignments intensified, these fields may have become more structured, encouraging the emergence of life forms tuned to their frequencies. And as alignments faded, just as today's dual-tail phenomenon of R2 SWAN or the unusual acceleration of 3I Atlas will eventually fade, these organisms lost the conditions necessary for their existence. But what if some of these beings did not vanish completely? What if fragments of their genetic or structural logic persisted, influencing the development of later life? Some studies suggest that fractal growth patterns present in ancient organisms appear again in modern systems. Vascular networks, neural branching, fungal mycelium, and even certain plant formations. These similarities may not be coincidental. They may represent echoes of ancient templates encoded into the fabric of life. In this sense, the enigmatic creatures of the Precambrian may still live within us, shaping how our bodies grow, how our neurons connect, how our cells communicate. If this continuity exists, then our evolutionary story begins far earlier and encompasses far more than we recognize. The comets overhead, the unusual alignments, the mysterious tail structures, these may be reminders of the conditions that once nurtured the earliest expressions of life's potential. And as we decode the fossils of these impossible organisms, we are not simply reconstructing biology, we are recovering fragments of environmental narratives shaped by celestial forces. These narratives may guide us toward understanding why certain life forms emerged when they did, and why consciousness eventually arose from a world so deeply intertwined with cosmic events. To trace this lineage further, we must examine not only organisms but entire environments, prehistoric landscapes that bear signs of disruption or transformation aligned with astronomical cycles. These environments may reveal how cosmic influences shaped Earth's geological canvas long before. To understand how prehistoric landscapes recorded these cosmic influences, we must imagine Earth not as the stable planet we know today, but as a world constantly sculpted by extraterrestrial rhythms. Long before dinosaurs existed, long before forests rose or oceans stabilized into familiar forms, Earth's surface was a dynamic canvas shaped by impacts, magnetic storms, atmospheric chemistry shifts, and cycles of cosmic dust deposition. Each cometary passage, especially those involving objects with unusual electromagnetic signatures, may have left imprints in the geological layers, subtle patterns that only now, through modern analysis, begin revealing their significance. Certain regions display stratified layers containing exotic isotopes not commonly found in Earth's crust, suggesting bursts of extraterrestrial material arriving at intervals. These intervals sometimes coincide with evidence of environmental shifts, oceans growing more oxygenated, minerals changing oxidation states, continents warming or cooling abruptly. Scientists attribute these changes to volcanism or tectonics, but the timing often hints at a trigger originating beyond the planet's boundaries. Imagine an early Earth landscape where entire regions shimmered with minerals charged by solar storms, amplified through cometary interaction. Imagine deserts of metallic sands reacting to electromagnetic pulses, lighting up under the influence of ionized particles released by celestial objects. These charged deserts could have acted as primitive circuit boards, their surfaces alive with electrical patterns that influenced not only atmospheric conditions, but geological processes. Some ancient sedimentary formations show ripple patterns inconsistent with typical water or wind erosion. They resemble wave interference, as if shaped by oscillating fields rather than physical currents. If early landscapes responded to cosmic frequencies, then features like these may be the geological footprints of energy passing through matter, signatures of celestial alignments now forgotten. One of the most intriguing possibilities concerns the role of comets in shaping mineral distribution. Certain precious metals and rare earth elements appear clustered in ways that suggest deposition from above rather than below. Their arrangement follows curved lines, spirals, or gradients consistent with particles entering the atmosphere at high velocities and dispersing according to magnetic or gravitational patterns. If cometary material delivered not only carbon and water, but rare catalysts, these catalysts may have gathered in specific regions, creating localized environments where early life found the chemical advantage needed to emerge. Geological surveys of ancient terrains reveal patches where mineral complexity spikes abruptly, zones where exotic compounds appear side by side with primitive fossils or unusual sediment structures. These zones behave almost like ancient laboratories, sites where the planet experimented with life under cosmic instruction. Another layer of evidence lies in ancient glacial deposits, where microscopic spheres of metallic origin are embedded within ice-formed sediments. These microspherules form when extraterrestrial particles vaporize upon atmospheric entry and then cool rapidly. Their presence in deep time layers indicates that early Earth endured periods of heavy cosmic bombardment. These bombardments would have altered climate, atmosphere, and surface chemistry in ways that could encourage evolutionary leaps. If celestial alignments intensified during certain epochs, Earth may have passed through regions dense with dust, debris, or interstellar particles, turning the sky into a conduit of transformation. More mysterious are the geological structures that resemble vast resonant chambers. Some caves, caverns, and hollowed-out mineral formations amplify sound, electromagnetic waves, or seismic vibrations. These natural structures, often formed millions of years before dinosaurs, behave like ancient instruments capable of resonating with environmental frequencies. If cosmic events produced waves that traveled through Earth's crust, these geological chambers may have amplified or modulated them, creating localized zones where energy accumulated. In such zones, minerals could form complex patterns, early organisms could respond to fields more strongly, and evolutionary pressures could intensify in unique ways. These chambers, some perfectly spherical, others hexagonal or conical, may represent natural antennas tuned to cosmic rhythms. Even more enigmatic are the polygonal formations found on continents and the ocean floor. Some resemble giant mosaics of interlocking shapes, much larger than modern polygonal ground normally produced by permafrost. Their scale suggests they were formed under conditions unlike anything seen today, perhaps influenced by extreme magnetic fields or repeated cycles of thermal expansion triggered by cosmic energy influxes. These formations are scattered across regions known for abrupt evolutionary transitions, as if the land itself shifted into states conducive to transformation. Some ancient landscapes also show signs of synchronized global change. Layers on opposite sides of the planet reveal similar transitions in mineral composition, suggesting they responded to the same external stimulus. Such synchronization is difficult to explain through tectonics alone, but becomes more plausible if driven by fluctuations in solar activity or cosmic radiation, both of which can be influenced by cometary alignments. The Earth's magnetic field, which shields the planet from high-energy particles, has reversed many times throughout history. These reversals often occur near geological and biological turning points. If interstellar objects distort the heliosphere or subtly influence solar output, they could trigger chains of events leading to magnetic instability. In this way, cosmic alignments might act as the metronome for evolutionary and geological cycles. The landscapes of ancient Earth also contain deposits of minerals that require unusual energy conditions to form. Some crystalline structures found in deep layers display patterns suggesting they grew under intense electromagnetic fields far stronger than typical geological processes would provide. These anomalies appear in clusters, as though entire regions underwent bursts of energy that rearranged mineral structures at the atomic level. If such bursts coincide with celestial alignments, particularly with objects carrying strong magnetic signatures, they may represent geological memories of these events. And if these memories shape the minerals that later interacted with early life, they may have influenced biological evolution from its earliest moments. Certain fossil beds show layers where organisms suddenly appear with new traits, greater complexity, branching forms, or novel body plans. These layers sometimes align with geological evidence of cosmic dust influx or atmospheric changes triggered by celestial phenomena. The coincidence is too consistent to ignore. It suggests that Earth did not evolve in isolation, but in partnership with the cosmos, responding to patterns repeated across deep time. If so, the landscapes themselves hold clues to prehistoric cycles of influence. By reading these landscapes as records rather than accidents, we may uncover the hidden conversation between Earth and the sky, a dialogue spanning eons, shaping matter, life, and consciousness alike. To follow this dialogue further, we must examine the forces capable of amplifying or muting these cosmic influences. Forces that operated before biological systems stabilized. Forces that may still operate today as R2 SWAN extends its twin tail, and 3I Atlas intensifies its alignment. Those forces emerge most clearly when we look at the deeper layers of Earth itself, where patterns of magnetism, pressure, and energy flow reveal how the planet once responded to. If we follow these forces deeper into the Earth, beneath the sediments and fossils, beneath the structures shaped by wind and water and time, we begin to encounter a world where the planet's memory is stored not in visible landscapes, but in the invisible currents of magnetism and pressure. The mantle, with its slow, churning rivers of molten rock, acts as a planetary heartbeat. The core, a sphere of iron and nickel generating the magnetic field, behaves like a colossal engine whose rhythms influence everything from atmospheric circulation to the migration patterns of life. These systems, ancient beyond comprehension, were forming and stabilizing during the same eras when strange Precambrian organisms appeared and vanished. Their development was not isolated from cosmic events. Each time a large comet approached, each time an interstellar object passed through the heliosphere, the planet's magnetic field shifted, strengthened, weakened, or pulsed with new currents. These changes reverberated through the mantle, altering temperature gradients, convection patterns, and even the chemistry of rising magma. In this sense, Earth's interior acted as a resonant chamber, absorbing and transmitting the influence of celestial alignments in ways that surface geology alone could not fully capture. Consider the magnetic field reversals, those mysterious flips where north becomes south and south becomes north. These reversals occur irregularly, yet certain patterns hint that they may correlate with periods of increased cosmic radiation or encounters with large celestial bodies. During a reversal, the magnetic shield weakens dramatically, allowing radiation to penetrate deeper into the atmosphere and even reach the surface. This influx of energy could have profound effects on early life, especially on organisms whose structures were sensitive to environmental fields. Some researchers suggest that magnetic reversals may act as evolutionary reset points, moments when organisms experience stress or mutation at levels significant enough to spur innovation. If so, comet alignments may have contributed to triggering these reversals, acting as external catalysts encouraging the planet to shift its magnetic configuration. Deep within the Earth, magnetic anomalies reveal regions where the field behaves unpredictably, where lines of force twist or weaken. These anomalies often coincide with ancient impact zones or crustal structures associated with cosmic influence. They act as scars, reminders of events that shook the planet's energetic framework. Over millions of years, these scars may have shaped the flow of magma, the rise of mountain ranges, the opening of oceans. In turn, these geological systems influenced climate, atmospheric chemistry, and the environments where early life formed. It is in this interplay between external stimulus and internal response that the seeds of prehistoric civilizations, if one defines civilization not by technology but by organized complexity, may have been planted. Some scientists studying deep mantle plumes suggest that the timing of major volcanic events aligns with cycles of increased cosmic influx. When interstellar objects enter the solar system, they bring with them dust and particles capable of affecting solar output or altering the distribution of charged particles in space. These influences cascade through the heliosphere and eventually reach Earth, where they can alter the stability of the magnetic field. If magnetic shifts weaken the boundaries between mantle convection cells, they could allow plumes of molten rock to rise, triggering eruptions or creating hotspots. These geological events reshape continents, redistribute nutrients, create new habitats, and wipe out old ones. In this sense, cosmic alignments may have played a role in shaping Earth's deep-time evolutionary path through mechanisms far more subtle and intricate than direct impacts. The influence of comets and interstellar objects on Earth's deep layers might also help explain the puzzling regularity of certain geological cycles. For instance, some studies suggest that major climate shifts occur at intervals that roughly match periods when the solar system passes through dense regions of the galaxy. These periods see increases in cosmic rays, interstellar dust, and cometary activity. If R2 SWAN and 3I Atlas are modern examples of such alignments, their presence may be part of a larger pattern, one that shaped Earth long before biological life took hold. During these ancient cycles, the planet's magnetic field may have fluctuated wildly, creating windows where early organisms experienced heightened stress or opportunity. Such conditions could drive rapid adaptation or extinction, paving the way for new forms of complexity. The possibility that Earth's interior responded to cosmic stimuli leads to an even more intriguing idea. If the planet's mantle and core act as resonant systems, then celestial objects with strong electromagnetic signatures could induce vibrational patterns deep within the Earth. These vibrations, akin to low-frequency sound waves, might travel through the mantle and crust, influencing fault lines, volcanic chambers, and even mineral formation. Such events could create periodic pulses of geological activity, subtle in some eras, catastrophic in others. These pulses would shape not only the planet's geography, but the evolutionary context in which life developed. In this view, the Earth is not merely reacting to celestial forces, but participating in a cosmic dialogue. Some ancient cultures hinted at this connection in their myths, describing the Earth as a living being that responded to the sky. While symbolic, these narratives may echo a deeper truth: that Earth's internal systems are sensitive to celestial rhythms in ways science is only beginning to detect. For example, the Schumann resonances, electromagnetic frequencies generated by lightning within the atmosphere, can be influenced by solar and cosmic activity. If such external forces can shape atmospheric resonances today, imagine their effects on an early Earth with a thinner atmosphere, a hotter surface, and a more active magnetic field. Even today, under intense solar storms, Earth's magnetic field vibrates, its lines of force rippling like a drumhead struck by invisible hands. These vibrations travel through the mantle, causing slight shifts in pressure and temperature. If modern Earth responds so sensitively, the primordial Earth, with its molten surface and highly conductive crust, would have responded far more dramatically. These responses may have created temporary conditions favorable for the emergence of new chemical systems or new forms of environmental intelligence. They may have shaped the strange fractal organisms of the Ediacaran era, encouraged the diversification of early microbial life, and carved environmental pathways through which biology could evolve toward complexity. If cosmic aligned forces shaped Earth's deep layers in this way, the implications are profound. It suggests that the story of life on Earth cannot be understood without considering the planet's interior as an active participant in cosmic cycles. It suggests that Earth itself may have incubated early forms of organized complexity influenced by celestial events. And it suggests that the alignments unfolding today, R2 SWAN's twin tail stretching sunward, 3I Atlas intensifying its approach, are not isolated astronomical curiosities but part of a pattern that stretches across eons. To grasp the full significance of this pattern, we must now rise from Earth's interior and look upward, toward the ancient skies where early organisms, landscapes, and even minerals reacted to phenomena that resembled. If we lift our gaze toward those ancient skies, we begin to understand how profoundly the heavens shaped not only the earth below, but the consciousness of all beings that would one day emerge upon it. For early organisms, long before vertebrates, before plants, before the stability of ecosystems, the sky was not a distant spectacle. It was an active force. The atmosphere of primordial Earth glowed with charged particles, lightning storms spanning continents, auroras so vast they stretched from horizon to horizon. In such a world, the passage of a comet or interstellar object was not a faint streak, but a transformative event. R2 SWAN, with its twin Sunward tail, and 3I Atlas, with its interstellar chemistry, demonstrate how much energy these celestial visitors carry. But imagine their ancient counterparts crossing the sky when Earth's atmosphere was thinner, more electrically active, and chemically unstable. Their influence would have been profound, visible not only in the heavens but felt across land and sea. Some Precambrian rocks preserve microscopic spherical particles, tiny glassy beads formed during high-energy atmospheric events. These spheres appear in layers corresponding to periods of cosmic bombardment, times when the sky may have ignited with plasma storms triggered by approaching celestial bodies. Such storms could alter atmospheric chemistry, change levels of greenhouse gases, and shift global temperatures. For early Earth, even slight changes may have opened or closed evolutionary pathways. Organisms dependent on specific field conditions may have flourished during these cosmic windows and perished when the skies quieted. The enigmatic Ediacaran forms, with their fractal geometries and surface-based nutrient absorption, seem almost engineered for a world shaped by atmospheric energies. Their symmetrical, radiating bodies suggest sensitivity to fields rather than reliance on internal organs. They appear as if they were designed to receive signals, to anchor themselves within the shifting electromagnetic tapestry of their environment. If the sky provided these signals, then celestial alignments became the invisible hand-guiding patterns of early evolution. We can see echoes of these interactions in ancient geological formations known as varves, thin layers of sediment deposited annually in lakes. Some varves contain unusual chemical signatures indicating atmospheric shifts that cannot be fully explained by volcanic or terrestrial phenomena. These shifts align with periods when the solar system passed through dense regions of cosmic dust, or when cometary showers intensified. If R2 SWAN's twin tail is any indication, such celestial bodies carry complex dust particles capable of altering light scattering, cloud formation, and even atmospheric conductivity. In an early Earth without stabilizing feedback mechanisms, these changes could trigger cascades that reshaped climates globally. And wherever climates shift dramatically, evolution responds. But evolution, in these early eras, was not simply genetic. It was environmental and energetic. The sky acted as an artist, using the planet as a canvas, with comets as its brushes. Ancient organisms were not merely passive recipients of these cosmic influences. Evidence suggests some species adapted to track environmental cycles tied to celestial events. Stromatolites, the layered structures built by colonies of ancient microbes, display growth patterns that correlate with day length, tidal forces, and even solar cycles. Their photosynthetic activity fluctuated with light intensity, influenced by atmospheric clarity. When cometary dust filled the sky, it filtered sunlight, altering energy available for these early life forms. The resulting growth slowdowns or accelerations are etched into the layers like planetary diary entries. If cometary dust influenced microbial behavior, imagine its impact on more complex early organisms, especially those attuned to energy fields. Some modern species still exhibit behaviors linked to geomagnetic or atmospheric variations caused by solar and cosmic activity. Birds navigate by magnetic fields. Insects swarm according to pressure changes. Microbes respond to radiation flux. These abilities did not appear suddenly. They grew from ancient origins. If prehistoric organisms evolved under a sky alive with cosmic signals, then magnetic sensitivity may have been one of life's earliest sensory capacities. Such organisms would respond to shifts in field strength caused by approaching celestial bodies. In this sense, R2 SWAN's sunward tail, or the subtle electromagnetic profile of 3I Atlas, would not have been abstract phenomena, but direct influences shaping life's behavior and development. Early creatures may have migrated, formed structures, reproduced, or entered dormancy in response to field variations now too subtle for most modern organisms to detect. Moreover, atmospheric changes caused by passing celestial objects could lead to periods of increased ultraviolet radiation, stimulating mutation rates. Not all mutations are harmful. Some provide evolutionary leaps. When cosmic rays increase, DNA repair mechanisms struggle, allowing new traits to emerge. In early Earth, this chaotic mutational environment may have produced the sudden bursts of complexity seen in the geological record. These bursts coincide with periods of known cosmic activity, suggesting that the sky was not merely a backdrop, but an engine of creativity. Ancient myths from cultures separated by time and distance describe beings descending from the sky, not as solid forms, but as luminous patterns, shapes of fire, or streaks dividing into two, strikingly similar to modern images of twin-tailed comets. These myths may preserve memories of atmospheric events witnessed by early humans, but what if the deeper symbolism, the sense that these sky beings influenced creation, is not symbolic but ancestral? Perhaps life itself was shaped by such celestial phenomena long before humans walked the earth. In this interpretation, humanity's myths are not inventions, but echoes of a memory far older than the species that speaks them. They are inherited intuitions about a relationship between sky and life that stretches back into deep time. Ancient cave paintings include swirling spirals, branching forms, and patterns resembling plasma discharges. These are often interpreted as abstract expressions or depictions of trance states. But some of these patterns match electrical phenomena that occur during intense solar storms or cosmic-induced auroras. If early humans documented the sky's behavior, perhaps they were preserving not only their own experiences, but the echoes of a far older language, one spoken by the Earth itself before biology became complex. When we see R2 SWAN's twin tail or the peculiar trajectory of 3I Atlas, we may be witnessing events that once played crucial roles in shaping early environments whose imprints still lie hidden in ancient sediments and fossils. To follow these imprints further, we must examine the organisms and early ecosystems that thrived during times of cosmic intensity. The strange beings whose forms appear too sudden, too organized, and too responsive to field conditions to be explained purely by Earth-based processes, organisms whose very existence suggests a world shaped not only from below by geological forces, but from above by, if early organisms were shaped not only by Earth's internal forces, but by celestial influences, raining down from above, then the ecosystems that emerged during these ancient eras may have been far more dynamic, ephemeral, and responsive to cosmic rhythms than anything we recognize today. These ecosystems were laboratories of experimentation, places where matter, energy, and environmental conditions collided to produce forms of life that seem almost impossible when viewed through the narrow lens of conventional biology. Some of these organisms appear in the fossil record for only brief intervals before vanishing completely. Others show bizarre adaptations that make little sense in stable, Earth-driven environments, but become more coherent if one assumes they evolved during periods of heightened cosmic intensity. For instance, certain Precambrian organisms display large surface areas relative to their volume, a trait ideal for absorbing energy directly from their surroundings rather than depending on internal organs. In a world where electromagnetic fields fluctuated more dramatically and where atmospheric chemistry shifted with each cometary encounter, such organisms may have been exquisitely tuned to environmental signals that no longer exist. These ancient beings, soft-bodied and fractal-branched, may have lived in transient conditions, shallow seas illuminated by frequent auroras, tidal zones where charged particles filtered into the water, and coastal environments receiving continuous energy from ionized dust. Their survival depended on responsiveness rather than internal complexity. When cosmic intensity peaked, their bodies could flourish. When it waned, they collapsed. This would explain why their fossil record is so episodic. They were not failures of evolution. They were expressions of a world in flux, creatures born of conditions that Earth no longer provides. Their existence marks an era when life may have been inseparable from the sky, when celestial events influenced not only climate or ocean chemistry, but the very architecture of living forms. And because these organisms lacked hard parts, they fossilized poorly, leaving behind only faint impressions, ghostly outlines hinting at a biology that responded to light, magnetism, and fields rather than simple nutrient flow. Some researchers have noted that these fossils often appear in sediment layers corresponding to unusual mineral compositions, suggesting that cosmic dust deposition may have created brief windows where specific chemical or energetic conditions allowed these organisms to thrive. Certain minerals found in these layers, such as iridium or specific rare earth elements, are associated with extraterrestrial sources. Their sudden presence could have acted as catalysts, enabling metabolic pathways impossible under normal Earth conditions. If the influx of these materials coincided with the passage of comets similar to R2 SWAN or objects like 3I Atlas, then early life may have risen in pulses synchronized with cosmic cycles. Ecosystem responses to these cycles would have been equally profound. In regions where atmospheric ionization was high, microbial mats may have bloomed in unexpected ways, producing oxygen spikes or altering local chemistry. These changes could ripple through the environment, creating pockets where early multicellular organisms could emerge. Such pockets, isolated and ephemeral, may have been the cradle for entirely new forms of life that flourished only as long as the conditions remained favorable. Their disappearance would not signify extinction in the traditional sense, but the closing of an environmental opportunity that had been opened briefly by cosmic influence. Modern analogs of these processes exist in small, extreme environments where life responds rapidly to changes in radiation or chemical availability. Microbial communities near hydrothermal vents flourish when mineral-rich plumes surge, then collapse when conditions shift. In frozen environments, microbes respond to small increases in UV radiation by producing pigments or altering metabolic pathways. These examples show that life is capable of remarkable flexibility when environmental signals are strong. Multiply that flexibility by the immense scale of Precambrian cosmic interactions, and the rapid appearance and disappearance of ancient organisms begins to look less like evolutionary mystery and more like environmental choreography. As early ecosystems responded to cosmic cycles, they may have developed structures resembling primitive ecological networks. Microbes that thrived under intense ionization might have served as the foundation for communities supporting larger organisms. These organisms, in turn, may have evolved traits optimizing energy absorption from field conditions. Some Ediacaran fossils show patterns suggesting they lived in clusters, forming networks where energy could be distributed across surfaces. These networks may have behaved like early biological circuits, responding collectively to environmental pulses. Intriguingly, some fossil beds show organisms aligned in consistent directions, as if orienting themselves according to magnetic fields or the position of celestial phenomena. This possibility raises the question of whether early ecosystems possessed a kind of distributed intelligence, not in the brain-based sense, but in the collective response to environmental information. Modern slime molds demonstrate that organisms without nervous systems can still solve complex problems by acting as networks. If early ecosystems operated under cosmic influence, their collective behavior might represent the first steps toward organized complexity on Earth. These early networks could have served as templates for later forms of life, embedding principles of cooperation, responsiveness, and energy optimization into biological evolution. And if these networks captured environmental information as they grew, they may have stored fragments of cosmic patterns in their structure. Some paleontologists studying Ediacaran fossils note recurring geometric motifs that resemble ancient field patterns, suggesting that the organisms grew according to environmental templates rather than genetic instructions alone. If true, then Earth's earliest ecosystems may have acted as memory systems, recording cosmic influence in the biological realm. At this point, it is worth pausing to acknowledge something crucial. If you are still watching, still engaged with this unfolding vision of a world shaped by cosmic rhythms, then you are part of a rare group, people who feel that the deep past holds answers to questions we have not yet learned to ask. If you want to help this investigation reach more minds who sense that mystery stretches far beyond recorded history, like this video and subscribe. Not as a formality, but as a signal that these forgotten stories deserve to be explored and shared. Because the next layer of this narrative takes us into environments even stranger, ecosystems that emerged during the dawn of early animal life, when cosmic forces collided with biological innovation to produce forms that seem almost alien in their structure and behavior. These organisms, rising after the fractal beings of the Ediacaran, would respond not only to cosmic events, but to, as the Ediacaran organisms receded from the stage of deep time, replaced by the first stirrings of Cambrian complexity, Earth entered a period in which evolutionary experimentation accelerated at a rate unparalleled in the planet's history. The Cambrian explosion is often presented as a biological mystery, a sudden and dramatic proliferation of body plans emerging from a world that had previously produced only soft-bodied, field-sensitive organisms. But if we view this transition through the lens of cosmic influence, through the lens of R2 SWAN igniting its twin tail and 3I Atlas threading interstellar memory through the solar system, then the Cambrian explosion may represent not an inexplicable leap, but a continuation of environmental responsiveness shaped by cycles far older than biology. In this view, early animals did not evolve in isolation. They emerged from ecosystems already shaped by cosmic rhythms, inheriting sensitivity to fields, light, pressure, and chemical gradients that operated long before bones, shells, or brains existed. These early animals were remarkably experimental. Some possessed compound eyes with more lenses than any modern creature. Others displayed spines, plates, and segmented bodies that seem almost too sophisticated for their era. Their sudden diversity implies not a slow buildup of genetic adaptation, but the unlocking of latent possibilities within Earth's biosphere. One theory proposes that escalating oxygen levels allowed for more energy-intensive life forms. But oxygen alone cannot explain the extraordinary variety of forms that appeared virtually simultaneously. What if the triggers behind these evolutionary leaps were not only terrestrial, but cosmic? Periods of increased cosmic radiation, dust deposition, or electromagnetic flux, caused by celestial alignments similar to those unfolding today, may have stimulated rapid mutation, developmental plasticity, and new ecological opportunities. Some Cambrian fossils show signs of structures sensitive to environmental fields. Certain organisms appear to have had staticists capable of detecting subtle shifts in orientation or gravity. Others had sensory organs that may have responded to polarized light, a trait useful in worlds where atmospheric ionization fluctuated dramatically. If the sky during this era was still influenced by cosmic activity, with auroras flaring at latitudes far from the poles and radiation levels varying according to celestial conditions, then early animals might have evolved traits that allowed them to navigate a world alive with cosmic signals. This environmental sensitivity would have been advantageous in oceans, where light penetration changed not only with depth, but with atmospheric clarity influenced by cosmic dust and charged particles. Consider the trilobites, among the most iconic creatures of the early Paleozoic. Their compound eyes, built from calcite crystals, were capable of detecting polarized light. This ability would have given them an advantage in locating prey or avoiding predators in waters impacted by cosmic conditions. Their bodies also show patterns suggesting sensitivity to magnetic fields, perhaps allowing them to navigate according to fluctuations similar to those caused by cometary interactions with Earth's magnetic environment. Trilobite mass migrations, preserved in certain fossil beds where individuals align in consistent directions, hint at behaviors influenced by environmental signals beyond simple instinct. Another intriguing example lies in the enigmatic hallucigenia, a creature so bizarre that scientists struggled for decades to determine which end was its head. Its spines and soft limbs suggest a body plan designed for environments shaped by fluctuating currents and shifting sediment. Such environments may have been common during periods when cosmic influences altered sea levels, atmospheric pressure, or tidal patterns. If celestial alignments influenced Earth's rotation or orbital eccentricity even slightly, the resulting changes in tides and currents could have created dynamic habitats where weirdness, not stability, was rewarded. But the Cambrian explosion was not merely a biological blossoming, it was an ecological reorganization. Predator-prey interactions emerged for the first time, driving arms races that produced shells, claws, and defensive adaptations. These developments required energy, a resource more available during periods of increased oxygenation and environmental flux. Cosmic dust deposition from cometary tails could have altered atmospheric chemistry in ways that elevated global oxygen levels, while bursts of radiation may have stimulated microbial activity. These changes, though subtle on geological timescales, could create opportunities for rapid ecological restructuring. As early animals evolved, their ecosystems diversified. Complex food webs emerged. Organisms developed the ability to burrow, filter feed, swim, crawl, and hunt. These behaviors required coordination, sensory integration, and primitive forms of awareness. If cosmic cycles influenced environmental conditions, then early animals were navigating worlds where the rules changed periodically. Their bodies reflect this dynamism. The sudden proliferation of sensory structures indicates organisms adapting to environments where information, light, sound, vibration, chemical cues, fluctuated according to cosmic events. This adaptability may be the true legacy of the Cambrian explosion. Fossilized trackways from this era reveal creatures moving with purpose, exploring environments shaped by forces beyond biological competition. Some trackways show patterns of hesitation, directional changes, or spirals, movements suggesting organisms responding to stimuli other than predators or prey. These patterns resemble modern behaviors triggered by electromagnetic or atmospheric changes. If early animals possessed latent sensitivity to fields inherited from their pre-Cambrian ancestors, then fluctuations caused by celestial alignments may have influenced their actions. In this sense, the behavior of these early animals may have encoded responses to cosmic rhythms. The geological record also reveals sudden collapses of Cambrian ecosystems, followed by rapid recoveries and new radiations. These collapses often align with periods of increased cosmic activity inferred from isotope anomalies. If the Cambrian world was sensitive to atmospheric or magnetic shifts, then cosmic cycles could have periodically destabilized ecosystems, clearing the way for new innovations. This pattern mirrors the episodic nature of cosmic encounters, brief periods of intense influence followed by longer periods of stability. The Earth's biosphere adapted to these rhythms, weaving cosmic memory into evolutionary history. Some of the most compelling evidence comes from the structure of early neural systems. The nervous systems of Cambrian organisms show complexity disproportionate to their evolutionary age. The rapid development of neural pathways, sensory organs, and coordinated movement suggests influences beyond simple competition. Radiation flux, magnetic field shifts, and atmospheric changes driven by cometary alignments could have provided the stressors necessary to favor organisms with greater environmental responsiveness. In this sense, the evolution of awareness, primitive but foundational, may have been catalyzed by cosmic conditions. As the Cambrian moved into the Ordovician, new ecosystems emerged, each more complex than the last. Coral reefs formed, creating stable environments capable of supporting diverse life. Yet even these reefs show patterns of growth and collapse that align with cosmic cycles. The presence of extraterrestrial isotopes in ancient reef layers suggests cosmic influence remained a factor in shaping Earth's biology long after the earliest animals appeared. If cosmic cycles influenced the rise of early animals, then the next stage of this story takes us to the organisms whose complexity and adaptiveness reveal even deeper interactions with environmental signals. Organisms whose evolution shows patterns too synchronized, too sudden, and too structurally elegant to be explained merely through random mutation or terrestrial shifts. To understand these forms, we must explore the ecosystems that flourished as these ecosystems matured and diversified through the Ordovician and Silurian periods. Life began spreading across environments once too unstable or inhospitable for complex organisms. Seas deepened, shelves expanded, continental fragments drifted beneath skies still occasionally stirred by cosmic events. And while Earth grew more biologically intricate, traces of environmental sensitivity inherited from earlier eras remained embedded within the physiology of emerging species. Some organisms evolved elaborate sensory structures not merely to detect prey or danger, but to perceive subtle cues from the environment. Currents, fields, vibrations, pulses of chemical or electromagnetic origin. These traits suggest that early life continued to operate within a world shaped by influences that extended beyond Earth itself. As comets like R2 SWAN and interstellar visitors like 3I Atlas demonstrate today, cosmic phenomena do not simply decorate the heavens, they interact with the planet at scales we are only beginning to understand. Take, for instance, the peculiar radiations that sometimes appear in Ordovician rock layers, spikes and cosmic ray indicators that correspond with known astrophysical events. These spikes precede periods of biological turnover, including the Great Ordovician Biodiversification Event. During this time, the number of marine species increased dramatically, ecosystems expanded in structure and function, and entirely new modes of life emerged. Standard explanations point to atmospheric oxygenation, tectonic activity, and climatic shifts. But what if these terrestrial processes were themselves responses to cosmic triggers? Increased cosmic radiation can change cloud formation, influence climate, and affect evolutionary rates. If interstellar dust or cometary debris periodically washed through the atmosphere, filtering sunlight or altering thermal gradients, then evolutionary windows could open abruptly, allowing new ecological strategies to flourish. Some fossils from this era show organisms developing complex eyes, sensory appendages, and nervous systems capable of detecting far more than physical contact or chemical gradients. They appear exquisitely adapted to worlds of shifting light, fluctuating ionization, and dynamic currents. If cosmic events influence these environmental conditions, then these sensory systems may have evolved partly in response to celestial rhythms. Trilobites, for example, diversified into hundreds of forms, each with specialized sensory abilities. Some possessed eye structures capable of detecting faint variations in polarized light, a trait particularly useful in waters affected by atmospheric disturbances triggered by cosmic dust or radiation. Their fossilized lenses preserve patterns that may reflect ancient interactions between sunlight and atmospheric particles of extraterrestrial origin. Similarly, the development of reef ecosystems during the Ordovician suggests environmental stability punctuated by sudden collapses. Reefs require precise conditions: light, temperature, acidity, nutrient flow. Yet many ancient reef systems show signs of abrupt decline followed by rapid recovery. These cycles coincide in several cases with fluctuations in cosmic ray exposure inferred from isotope analyses. If cosmic events periodically altered the climate or ocean chemistry, reefs would be among the first systems to respond. Their growth patterns could thus serve as records of ancient cosmic cycles, preserved in limestone like the echoes of forgotten astronomical alignments. As ecosystems expanded, organisms began exploring new ecological niches. Some adapted to deeper waters, others to nearshore environments influenced by tides and atmospheric conditions. This diversification reflects not only biological innovation, but environmental opportunity. If the sky periodically altered the composition of the atmosphere or the energy penetrating the ocean, certain regions would experience sudden ecological openings. Species capable of exploiting these openings rapidly diversified. This pattern resembles the episodic nature of celestial alignments, brief periods of influence followed by longer intervals of equilibrium. Even more intriguing is the emergence of early terrestrial ecosystems. The first plants, fungi, and arthropods to move onto land-faced environments exposed directly to cosmic radiation and atmospheric variability. Their bodies evolved protective pigments, structural adaptations, and metabolic pathways that suggest sensitivity to UV fluctuations or ionizing radiation. Some early plants show rapid shifts in morphology that correlate with periods of atmospheric change preserved in ice core proxies and sedimentary sequences. If cosmic events influenced atmospheric transparency or cloud coverage, early terrestrial organisms would be directly affected. Their evolutionary patterns may thus contain faint signatures of cosmic memory. The expansion of terrestrial life also introduced the possibility of organisms responding to magnetic cues, a trait still present in many modern species. Magnetoreception in birds, insects, and even some mammals is widely documented, yet its origins remain obscure. If early terrestrial organisms evolved under skies influenced by celestial alignments, then magnetic sensitivity could have arisen as an adaptive response to shifting field conditions. Fossils of early arthropods show patterns of alignment similar to those found in modern migratory species, suggesting that environmental cues may have guided their behavior. These cues in prehistoric eras shaped by cosmic rhythms could have included subtle variations in Earth's magnetic field triggered by celestial objects passing through the heliosphere. As life continued its march toward complexity, entire ecosystems began forming feedback loops that amplified or dampened the influence of external forces. Plants altered atmospheric composition. Microbes influenced soil chemistry. Animals shaped nutrient cycles. Yet these feedback systems were not isolated from cosmic input. They amplified its effects. Increased radiation could influence plant pigmentation, altering heat absorption, affecting regional climates, and changing the ecological opportunities available to animals. Dust from cometary tails filtering sunlight could alter photosynthesis rates, affecting entire food webs. Magnetic shifts could influence migration, reproduction cycles, or metabolic rhythms in species sensitive to environmental signals. These interactions hint at an underlying principle: that Earth's biosphere, from its earliest days, evolved not only in response to geological and biological forces, but within a larger cosmic framework. Each evolutionary leap, each ecological transition, may have been influenced by interactions between Earth and the celestial objects that occasionally passed near it. The presence of unusual comets today, like R2 SWAN with its twin Sunward tail, may be reminders of these deep time dynamics. Their rare appearance prompts us to consider the possibility that such alignments occurred in ancient eras, influencing environments and shaping the trajectory of life. If we view the fossil record through this lens, sudden transitions become less mysterious. Bursts of complexity, abrupt collapses, and periods of rapid diversification may reflect cosmic rhythms interacting with Earth's internal processes. The next step in tracing this hidden story lies not only in the biological realm, but in the myths and symbolic memories carried by early human cultures. Stories of sky teachers, twin-tailed stars, and celestial visitors that resemble finally, as we return from the fossil record, the ancient skies and the restless interior of the Earth. We arrive at the threshold where science, myth, and deep-time memory converge. Here, in this liminal space between knowledge and possibility, we encounter an idea as old as humanity, yet rooted in epochs that long preceded us. The notion that the stories early humans told about the sky, their myths of twin-tailed stars, wandering cosmic messengers, and celestial teachers descending to shape the world, may not have originated in the human mind at all. Instead, these myths may be the final echo of a memory carried forward through biological evolution and geological transformation. A memory not of human civilizations, but of prehistoric worlds shaped by cosmic rhythms so powerful that their influence still resonates in our instincts, our dreams, and the symbols carved into the earliest stones. When ancient cultures spoke of beings arriving from the heavens, when they described stars splitting into two luminous streams or objects traversing the night sky with unnatural brilliance, they were speaking in the language of memory. Memory filtered through the limits of early consciousness, yet still anchored in experiences that echoed events in Earth's distant past. Patterns repeat across continents. Australian petroglyphs depict split-tailed comets identical to those etched into Andean stone. Early Sumerian myths describe wandering star beings delivering knowledge and then departing, leaving the world altered. Even older traditions, oral stories carried by cultures whose origins stretch into prehistory, contain descriptions of skies transformed by luminous visitors. When cultures separated by oceans and tens of thousands of years share nearly identical imagery, we are left with two possibilities. Either coincidence crafted these parallels, or they draw from a source older than humanity itself. And if the organisms that lived before the Cambrian explosion, before bones or shells or complex brains, were influenced by cosmic patterns, those influences may have carved themselves into the fabric of biological life. The instincts, fears, and fascinations that guide living beings today, including our persistent fascination with the sky, may be the evolutionary echo of worlds shaped by cosmic cycles. As early humans evolved, their minds became capable of reflection, symbolism, and narrative. Yet the environment that shaped their ancestors had already been tuned by celestial events for billions of years. If the earliest organisms responded to electromagnetic fields and atmospheric changes triggered by cosmic encounters, vestiges of this responsiveness could persist in the nervous systems of later species. The human brain, with its sensitivity to light cycles, magnetic variations, and environmental cues, may retain a faint whisper of ancient capacities once crucial for survival. And when early humans looked at the sky and saw comets, auroras, or unusual celestial alignments, something deep within their biological memory may have stirred. A recognition not intellectual but instinctual. A sense that the cosmos was not separate from life but intimately woven into its origins. This may explain why early civilizations treated the sky as a living calendar. Why they built monuments aligned with celestial events. Why they saw comets not as random wanderers but as messengers or warnings. Their myths preserved patterns their ancestors could no longer explain, yet still felt compelled to remember. These stories became the scaffolding for culture, religion, and identity. But beneath the symbolism lies a deeper truth. The sky had shaped the earth long before humans appeared. It shaped the minerals, the oceans, the atmosphere. It shaped the first organisms, the first neural networks, the first ecosystems. And if those early worlds were influenced by celestial alignments, then human myths may be cultural translations of biological memory. Memory that originated not in human history, but in pre-dinosaur epochs when cosmic forces sculpted the foundations of life. Even today, scientific studies reveal that cosmic rays influence cloud formation, atmospheric chemistry, and genetic mutation rates. Solar cycles alter magnetic fields and atmospheric currents. Cometary dust can seed clouds, filter sunlight, and deliver new chemical compounds to Earth. We observe these processes through satellites and instruments, but in the ancient world, they were witnessed through sensation, intuition, and storytelling. When R2 SWAN spreads a twin tail, or when 3I Atlas enters the solar system carrying interstellar dust, we see them as astronomical events. But ancient eyes would have seen signs. The same kinds of signs their ancestors, human or otherwise, once experienced as environmental transformation. This perspective does not suggest that prehistoric civilizations, in the human sense, existed before dinosaurs. Rather, it proposes that organized complexity, proto-civilizations of ecosystem intelligence, mineral networks, and environmental responsiveness may have developed long before biological minds emerged. These systems may not have built cities or tools, but they shaped landscapes, stored information, and responded to cosmic stimuli with coordinated adaptation. In this sense, Earth itself may have been home to civilizations far older than biological life. Civilizations composed of fields, patterns, flows, and resonances. Civilizations whose memories still whisper through the geological record, visible in isotopic anomalies, magnetic reversals, fossil bursts, and atmospheric signatures. If this is true, then our fascination with the sky is not curiosity, but inheritance. Our drive to decode the heavens is part of a legacy stretching back into pre-Cambrian oceans, into mineral matrices that once resonated with cosmic frequencies, into ancient ecosystems that pulsed in harmony with celestial cycles. And as comets cross our skies today, as rare alignments unfold in our lifetime, perhaps something deep within consciousness stirs again. A recognition older than humanity, older than mammals, older than the forests and mountains that now define our world. If this journey has expanded your sense of time, of life, of the mysterious relationship between Earth and the cosmos, share this video and subscribe, not merely to support the channel, but to help others rediscover the forgotten story written in fossils, stars, and the silent memory of the planet itself. Because the next time you look at the night sky, you may feel that the comets moving across it are not strangers but